I'm Kirk Harnack. On This Week in Radio Tech, Chris Tarr and Chris Tobin join me. We're talking to Bob Orban. That's next on This Week in Radio Tech.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for This Week in Radio Tech is brought to you by Cachefly at CACHEFLY.com.
This is This Week in Radio Tech, episode 110, recorded December 14th, 2011. Bob Orban. This Week in Radio Tech is brought to you by the Telos Alliance and the astonishingly gorgeous Now catalog, featuring color pictures, diagrams, techie specs, and many words of modern radio wisdom. Telos will mail it to you for free, and you can download the PDF. Get yours at telosalliance.com/now. Hello, it's time for This Week in Radio Tech. I'm your host, Kirk Harnack. If you've tuned into this show, you probably already know what it's about. It would be Radio Tech. We're a bunch of engineers that get together every Wednesday at this time on the Twit Network and talk about the things that go into radio technology. It may be audio. It may be good audio or fixing bad audio. It may be just assembling all the things that bring audio into an audio facility, usually a radio station, and or maybe a netcaster like the folks at the Twit Network who are also adding video to their work. Or it may have to do with things at the transmitter site, that is getting this audio out to the masses of people that radio tends to touch. So without further ado, let me introduce my co-hosts on the show. First of all, the best-dressed engineer in radio from Manhattan, New York. It's my friend, Chris Tobin. Make him feel welcome. Hello, Chris.
Hello, Kirk. I'm doing well, and New York City today is doing very better. A lot of dignitaries in town, not sure why. So the radio folks here in town have been running around. The radio news folks are all over the place. So it's been a busy day.
I'll bet. And you were, up until recently, were an engineer with the CBS radio stations. And I know you've had just a ton of radio engineering, but now you've got a little bit different role in life, but still gives you a good perspective on broadcast engineering, though. Tell me about that quickly.
Yes, I've taken over the reins at CCS Musicam, codec manufacturer, audio over IP and video over IP. And actually, I get to dabble even more now with radio folks. It's a lot of fun, both engineers and non-engineering types. And more IT people, interestingly enough, changing hats and roles. So it's been fun. It's really good.
Oh yeah, years ago somebody told me, in the future we won't have TV cameras anymore. We'll have computers that make TV pictures, and we won't have transmitters anymore. We'll have computers that transmit. And it does seem like we are certainly along that direction. As we have audio processors, as we'll talk with our guest Bob Orban, we'll talk about computers that process audio. Also with us from the northern hinterlands, out in the wild, wild Midwest, from Mukwonago, Wisconsin, it's Chris Tarr. Hi, Chris.
Hello there. Yeah, we don't have any dignitaries here except for, I think, Miss Dairy Air stopped by earlier today, or in Mukwonago. But other than that, it's been pretty quiet. I am the Director of Engineering for Intercom's radio stations in Madison and Milwaukee. I'm also a contributing writer to Radio Guide magazine, co-host the website The Virtual Engineer at broadcastengineering.info, and a whole lot of other things, as well as probably one of Bob Orban's biggest fans.
All right. Well, I think we're all Bob Orban fans here. I certainly got my start in the first stations that I worked at. Had Orban OPTIMOD 8000s. And here we've been talking about the guy. I mentioned his name a couple times. Let's introduce him. It is Bob Orban from Orban.com and the Orban Processor Company. Hi, good evening, Bob. How are you?
I'm doing well, and thanks for having me.
Well, it is our pleasure, and I'm glad that we, before you on the show, had some of your friends like Bill Sachs and Greg Oganowski, and now we've got you on the show. I'm looking forward to this next hour where we will really get to talk about some of the innards of audio processing. We're going to try to scoot through a little bit of history here pretty fast and talk about some of the developments that you've come up with. One of the things that I wanted to ask you, Bob, right away is the very first product that you came up with, and that's the stereo synthesizer. We were talking in the pre-show about the fact that this was a product that I used on a station. I had a radio station that we had bought in Mississippi. It was an FM station. And at that exact moment, we had to take control of the station and put up a studio transmitter link, 950 megahertz link. The only one we had was purely mono. It wouldn't carry the FM stereo baseband. And we had to produce our programming over in Cleveland, Mississippi. The transmitter was over in Drew, Mississippi. And mono was all we had. So at the transmitter site, we took this mono audio, ran it into an Orban stereo synthesizer, and out of that box, out of that stereo synthesizer, came a reasonable facsimile of a believable stereo signal, which then went into our audio processor, which was an Orban 8000, and then in the transmitter. What was your idea in coming up with such a box, Bob?
I had actually worked on that at the student radio station at Princeton. The reason being that we had a top 40 show from 4 to 6 p.m., and we had a FM stereo signal, and very few of the singles were being mixed in stereo at the time. There was often a album version that was sort of a throwaway mix, but the sound of the single was the sound of mono. So we wanted to be able to have a sort of accurate top 40 show that was also stereo. And to do that, I needed something that would spread out the mono a little bit and still have mono compatibility. And it occurred to me that the way to do this might be to basically synthesize a different signal with an all-pass filter. An all-pass filter is just a phase shifter. If you measure the frequency response, it's flat, but if you measure the phase response, it's very non-flat. And if you create an artificial L-R, it turns out that not only is the signal mono-compatible in mono radios, but also the some of the power spectra of the left and right channels are the same as the power spectrum of the mono. So regardless of whether you're listening in mono or stereo, you still get the same frequency balance, and it's the balance that you associated with a hit.
Wow. Okay. I didn't know all those factors went into synthesizing stereo. And you said something that you know, we as broadcast engineers toss around quite a bit, but let's introduce our audience, those who may not know of this concept, mono-compatible. What does that mean, and why would you be, what happens if something's not mono-compatible?
In radio, bad things happen. People think, well, you know, FM radio is stereo. The fact is that every auto radio has a blend function in it, and usually what it does is it looks at some metric of the RF channel, whether it's signal strength or multipath or something, and will blend the stereo channels back to mono if the signal gets too bad. So to this very day, mono compatibility is still a very important aspect in a you know, radio-ready mix.
Gotcha. I would imagine that myself and Chris Tarr and Chris Tobin, co-hosts on the show here, I'm guessing that all of us became familiar with Orban, with the Orban 8000. At least that was my first one. Maybe Chris Tarr, being the young buck here, maybe he started with the 8100. Chris Tarr, what was your first experience with an Orban?
Actually, it was well, the first Orban was an 8000, but I seem to remember there may have been a Duro DAP in front of it.
Sure.
I do remember there was something ahead of it. I don't remember what, but I was just a child when I saw that.
Well, actually, I've walked into engineering at some stations where people thought they needed to put the UREI LA4 in front of the OPTIMOD 8000. And then people also thought they needed to put the CP803 composite clipper after the 8000. So it oftentimes, you know, the Orban OPTIMOD 8000 was sandwiched between other stuff.
I think that's gone on for years. I mean, look at how many people have stacked things like, you know, multiple volume X and Automaxes on a chain.
So I want to go to a basic question here for Bob. You know, prior to your development of the 8000 and the original OPTIMOD FM, Bob, I think you've explained on the Triangulation show and in other venues that before that time, the processor and the stereo generator for FM were different boxes. Yes. And maybe you could walk us through that a bit. And why did you have this idea that that's not the best way to do it?
Well, the FCC rules were quite strict at the time. They required transmitters to be type accepted, I think it was. I never remember the difference between type accepted and type approved, except that I know one of them you actually had to send the box to the commission for measurement. The other one you could do the measurements yourself, if I recall correctly. But the point being that the stereo generator was part of the transmitter, so the stereo generator was type accepted. And about the time that the 8000 was developed, Mosley came out with its first composite STL. So this was something new in the signal path. It was a output of a stereo generator that went over a microwave link and thence to the transmitter. So the FCC finally sort of got the idea that maybe it's okay to disengage the stereo generator from the transmitter. Eric Small took this idea and ran with it. He basically took the idea of the 8000 down to the FCC. I think he talked to Harold Cassens, who was a major engineer at the time, and persuaded him that if we did type acceptance measurements on the stereo generator inside the 8000, that there should be a general approval that that could be used with the exciter, the FM exciter within the transmitter. In addition, there was just a very long tradition of starting with something like an AGC or a compressor, and then the peak limiter was a separate box, could even be a different brand. Like some people would use an Audimax with the Audimax being the compressor, using that with a GE look-ahead limiter or Collins. And then there was another wire at the output of the limiter, and that would go into the transmitter, which was implicitly the stereo generator. And all of these wires and interfaces were non-ideal. First of all, it was easy to really mess up the adjustment so that you could actually get headroom issues in the circuits. And second of all, as I discussed with Leo a while back, the low-pass filters in the stereo generator would overshoot and ring. And this was the main cause of loss of peak modulation, or I should say loss of average modulation. It was an increase in peak modulation caused by the overshoot and ringing.
Sure.
So the opportunity arose to put all of this stuff under control. Put raw audio into one side of the OPTIMOD, take a FM stereo composite out the other side. We got rid of the ringing and the 15 kilohertz low-pass filters, and we got rid of any interface problems just caused by, say, a level or, transformer problem between the limiter and the stereo generator. We had one set of transformers and an 8000. They were at the input. After that, it was pretty much direct coupled, as I recall. So it also had no problem with low frequency bounce and tilt to speak of. That's another issue, which we could get into later if you want. But basically, the fact that the transmitter had a response to 50 hertz, which was all the FCC required, was insufficient to preserve the peak modulation control of highly processed audio. And In fact, it turns out that you need to have significant response down to 0.16 hertz, 1.6, in order to have a minimal amount of low-frequency tilt and to get the best amount of modulation control. And the 8000, if I recall correctly, had only one coupling capacitor, which was at the output of the stereo generator. I do not think it was quite 0.16 because we hadn't done the math on it at that point, but it was down there. And so 8000s did control modulation pretty tightly.
Can you help me understand one thing? I've not, with AM transmitters, I've understood a low frequency tilt, that the AM transmitter modulator and amplifiers may not be able to, maintain a square wave that's a low frequency. But what is low frequency tilt in the world of FM modulation? What does that look like, and how does it manifest itself, and why does it cause a problem?
Well, the moment that you get clipping into the picture, you start to make square wave-like audio waveforms. And if you happen to have a lot of bass energy and you hit the clipper, you get something that flat tops, and it may flat top for a relatively long time interval. Technically speaking, you're actually generating difference frequency intermodulation below the frequency range of the input audio. But mainly, tilt is important because you do clipping-like operations. It's a little bit more complicated than that when you get into the details, because the high-pass filter that you get when you just create a series capacitor and resistor to ground, that has an associated phase shift with it. And even if you don't hard clip a waveform, you can still change the phase relationship between low frequency energy. If you have more than one frequency component, down below 100 hertz, you need to have those all lined up in a certain way in time in order to avoid having overshoot happen. So you want to avoid phase shift in addition to just dealing with the issue of the difference frequency IM down there.
I've got one more question before I think Chris Tobin has a question he's going to ask. But here's mine. When you were designing the Orban 8000, or your first real FM processor here, what were you at the time working with? What was considered state-of-the-art integrated circuits, and were you developing circuit designs that were maybe not in a textbook, that were improvements on what had been taught in electronics courses?
I had introduced ICs into the picture fairly early. Fairchild came out with a IC op-amp called the 709. And the 709 had a bunch of problems, but one thing that was good about it was it had a very simple input stage, and the input stage was quite low noise. 709's big problems were, first of all, that it needed to be externally compensated, and second of all, that it had a Class B output stage, so you get a lot of crossover distortion. But it was possible to put a pull-down resistor at the output of the op-amp to the negative 15 supply to bias into Class A. And then you had yourself a pretty linear, low-noise amplifier. And in fact, we used 709s as the buffer amps for our FET gain control elements in the original 8000. The signal level in a processor like that actually goes down to about 20 millivolts or so. It's really sort of almost phono cartridge level. So you have to do quite a bit of low noise design to get it to work very well. And as I recall, we were able to get something in the order of 80 dB noise floor in the device, and much lower input to output distortion than the previous generation of processing could do, mainly because we didn't have any transformers in the path, and because we used IC op amps instead of discrete transistor amplifiers.
In the chat room, Navion reminds us that these were typically in a can with 8 leads coming out of them. Isn't that right?
That's absolutely correct.
Wow.
The 8-pin dips really didn't come out until a while later. Originally, these IC op amps were quite expensive. Fairchild made them in 2 temperature ranges, one for commercial and one for military. But for the sake of reliability, they wanted to keep the chips hermetically sealed so that there was no possibility of having moisture leak into the chip and compromise the integrity of the metallization or the leads going to the final 8 big wires coming out. So that was really the history behind the metal cans, and the 8-pin dips were a cost reduction measure. But we actually got bit really bad by some 4558s, which we used a lot in the early Orban products. I forget whether it was a National or somebody had moved the line, I think, to Mexico, and they had some contamination, and they created basically time bombs that would work for a couple of 100 hours, and then they would just go belly up. So this was, some painful learning experience. Fortunately, the IC manufacturing industry has greatly moved on since those days.
Chris Tobin, I think you had a question from your perspective in New York City, where you surely have cut your teeth with OPTIMODs there.
Oh, OPTIMOD, yes, definitely. From my college days, where we had the Mike DeRoe box, and then we had the 8000. And here in New York City, in the Metro, it's it was always about loudness wars, which I don't think it's changed any. But one thing I wanted to ask was the design. Back in my early days in my career, I did a lot of patent reading, so I read the patents on your boxes, and they're absolutely genius. How did you come to the idea of the smart clipper in the 8100? I'll move forward from the 8000 to the 8100 series. And, the idea behind that and the way you did it. I know there's a lot of little black epoxy boxes on the circuit board, but just how did you even think to, go in that direction, realize what you can benefit from, and how you can make basically the works in the drawer box just, the ultimate when it comes to, being competitive, being soft, everything about it. It's just brilliant, the whole design. I'm just curious. The smart clipper has always fascinated me. I've always worked around it and morphed it into other things, moved it around with other boxes, as Chris Tarr was saying. So how did you think about that? Or, just something you came up with one day in the backyard or sitting with a piece of paper? Just curious.
That set of ideas actually started with OPTIMOD AM 9000. I had decided to try to put a steep slope equalizer in our first AM processor to somewhat equalize out the 2 kilohertz slopes that typically were found in the IF stages of the car radios of the day. And when I tried to run a preemphasized signal like that into a hard clipper, it sounded awful. And you got the S's turning into F's, as I discussed on the previous show here.
Oh, yeah, yeah.
With Leo. And so I thought, well, what would happen if I low-pass filtered the distortion coming out of the clipper and then subtracted it from the clipped signal, thereby canceling the clipper distortion, below about 2 kilohertz. Originally, this was done with analog bucket brigade delays because the low-pass filter at 2 kilohertz had a fairly large group delay, particularly because there was some group delay equalization in it. So that was the start of the smart clipper. The 9000 actually also had a psychoacoustic model in it. There were a lot of interesting new ideas in that box. We above 2 kilohertz, we divided the mid-range into, I think it was 5 or 6 third octave bands, and we looked at the ratio of the distortion signal caused by the clipper to the undistorted signal. So we estimated whether the clipping distortion would be psychoacoustically masked, and then we used a sort of look-ahead limiter design so that the drive level to the main clipper in the box could be actually turned down before it produced the distortion. And this was, pretty hot stuff at the time, because this was 1977, and these ideas were later used in audio codecs, but that really didn't start to be well known until I think around 1979 to 1980. So going from the 9000 to the 8100, the problem with bucket brigades is that they had limited noise and distortion performance. It was fine for AM, but not what we would want to have for FM. So it occurred to me that you could use the 15 kilohertz low-pass filter of the OPTIMOD as the matching delay element for the 2 kilohertz distortion canceling filter. Required a lot of group delay equalization, some fairly fancy mathematics to design the filters. They were all numerically optimized. But the result was that we got typically around 30 dB of cancellation, and because there was no bucket brigade in the system, we were able to get a very high quality audio path.
That was brilliant design, I have to say. And it's still to this day, is still a brilliant design.
Well, thank you.
Chris Tarr, you had a question you were raising your hand over.
Yeah, this is it's a combination technical and philosophical. I've been a big follower of yours for a long, long time, and I studied a lot of your white papers. And one of the things that I still do to this day when I set audio processing and have intelligent discussions with my program directors about is something you put, and I believe it was even as far back as the 8000 manual, or in one of your white papers about the audio in your plant. You always talked about how radios have a volume control, but they don't have a control to undo distortion and things of those nature. And I know that in the original design of the OPTIMODs with the 8000 into the 8100, it was a conscious decision on your part to limit the amount of controls available. It was one of those where you didn't. In other words, it was very hard to make an 8000 or 8100 sound bad. You would have to really work at it to make them sound bad. Now, we go progressively on through the 8200, 8400, 8500, 8600, and it's gotten to the point now where if you really want to get down to granular controls, you can do that on an 8500. There is a whole lot of things you can adjust on those systems. How do you feel about that? Because again, you're a hi-fi guy, and you've always been about quality over loudness. Loudness has not been the big thing. I mean, it's been part of it for competitive reasons, but I know that personally you're into the to a nice high-quality musical sound. Was it and without having to go too in depth? Has that been difficult to release some of that control to people, knowing that it could be used for evil as opposed to good?
It took a while to get used to it. I do happen to agree with Steve Jobs about the importance of the user experience. And one of the reasons why the 8000 and the 8100 had as few controls as they did was exactly what you said, that it was very hard to make them sound bad. And even when we added the XT2 accessory chassis to the 8100, that didn't have a huge number of controls available. It wasn't until our first DSP-based processor, the 8200, that I felt that we could take advantage of digital technology to keep the user interface and experience simple and elegant while still offering more control to the user. So one of the two main things that we introduced for the 8200 were, first of all, quick setup, which was a wizard-like guided setup that took you through from the beginning to the end, and hopefully got you on the air with a appropriate sound for your format. And the second important thing was one knob less, more control. Under the hood, using digital processing, we sort of conceptually had about 50 different rubber bands and belts moving all the controls. But we had already optimized the what are really a family of presets under one factory preset name, so that you could trade off loudness against distortion while still maintaining the optimum trade-off and not getting too far afield. As we moved forward with the 8400, 8500, and 8600, we had to respond to the realities of the marketplace, which were that competing processors were giving more of these controls to the users. But we always kept quick setup, and we always kept less, more, so that the ideal of the bulletproof processor hopefully has been carried through right up to our current product line.
Unmute there. Fantastic. Now, and just a quick follow-up too. With your again, I've talked about your training in the past. There is a very different sound between an OPTIMOD and even and Omnia and all these different kinds of processors. And I describe the OPTIMOD as having kind of a very foolish sound. And I'm just wondering, in your design, is there kind of a certain sound that you kind of have, that you have in your head? I seem to think that over the years, although some of the controls have changed and the amount of loudness and things have changed, the overall sound of an OPTIMOD has always kind of been the same. It's always been a kind of a musical thing, as opposed to, there's the Omnia, for example, has a very specific sound. It's also musical, but in a different way, and there's a very distinct difference there. And I'm wondering, is that kind of just based on, you have in your head kind of an ideal radio station sound? Do you design to that?
That's a complicated question. I've known Greg Oganowski, who is our VP of new product development, for a long time, and he and I share a lot of preference when it comes to the sound of radio stations. So my original multi-band processor was the 8000. It had 6 bands, and it used steep crossover slopes, which allowed the processor to do quite a bit of automatic re-equalization of the program material. The crossovers were all pass. They weren't phase linear, which is something that comes with that territory. It means that the crossover points are at -3 dB and not -6. So some of the fatness of the OPTIMOD sound is still a secret sauce, but some of it has to do with the fact that we typically use all-pass crossovers and steep slope crossovers, except for the digital radio processors, where we do use steep slope crossovers, but they are phase linear.
Right.
I don't hear Kirk.
Can't hear you, Kirk.
How about that? There we go.
Much better.
I'll learn how to use this Skype one day. Bob, I'm wondering if you can talk about this this trade-off between distortion and loudness. And I know a lot of us as engineers get that, because loudness, can be made from distortion. That's what helps us perceive that. what can we as engineers, how do we talk to program directors about this trade-off? And how do you know when the distortion is too much? There was a there was a guy at a radio station here in Nashville who was talking to his engineer about distortion, and the engineer wanted a very clean sound, and the program director always wanted something louder, something louder, something louder. And there's a story that the program director was drinking a cup of coffee, and the engineer knew that this discussion was going to happen, so he brought in a little bottle with a dropper in it, and they had this discussion, and the engineer said, "Well, tell you what I'll do." And he opened this bottle dropper. He says, "I've got a bottle here full of urine, and I'm going to start dropping it into your cup of coffee, and you tell me when to stop." So, "What? Don't do that." Well, that's like distortion and loudness. Now, how much distortion do you want? What are your thoughts on that, Bob?
It depends on the format. I think that the most careful research ever done in the history of this business on that trade-off was done by Jim Schulke, who was the beautiful music syndicator who controlled literally every aspect of the air chain, all the way from the play-out system through the console, through the audio processor, through the transmitter, through the antennas. He felt that different antennas sounded different. I don't know how much of this was imagination and how much was, one antenna might have a little more, visor than the other, which causes more incidental AM and on. You could talk about that all day. But he managed to have an awful lot of #1 radio stations. I think that a lot of the problems with PDs asking for distortion is that often the audio processing is the least researched part of the air sound. That the program material is researched, they may do call-outs, they may do this and that, but you don't hear very often people being taken into focus groups and being asked to listen to various amounts of distortion in the audio processing. So you sort of have to make some generalizations about format versus the amount of distortion. You want to increase time spent listening. Conventional wisdom is that you reduce the amount of distortion. Increasing cume, conventional wisdom is you can tolerate more distortion for the sake of loudness if you only want to hear. I want people to listen for 10 to 15 minutes at a time. But I think a lot of it is, urban legends, a lot of it's gut feel. A lot of it is the least scientific part of radio programming at this point.
How much of what we, as an engineer, I grew up really thinking I understood this trade-off between loudness and distortion, and yet I believe that both Orban and Omnia and maybe some other companies too are learning about how to get louder and louder and louder while controlling or hiding or mitigating the distortion in certain ways. What are your thoughts about that comment?
Well, it's true. Our latest FM processor uses a psychoacoustic model to improve the loudness distortion trade-off by quite a bit. It's similar to the psychoacoustic models used in many of the psychoacoustic codecs these days. Its ancestor really is the 8000, where we did it for the first time. But by building more and more intelligence, in other words, information about how the ear actually perceives distortion into the processing, we can improve the trade-off in a way that was previously just impossible.
Bob, in about 15 or 20 minutes, we're going to run out of time, and that's such a shame because I know that there are engineers out there listening and watching who would love to hear so much more. Here's a question that's always been on my mind, and I guess it harkens back to the days when you guys started developing the 8200 processor. and I know you've talked about this in some of the forums in broadcasting, some of the listservs. What's it like designing audio processing in DSP instead of with analog circuits? And I want to add that a little while ago you were talking about these numerically optimized filters that you were designing, and that was all in analog that you were talking about at that point. How is the world different when you get to use DSP, and maybe even is there anything worse about designing in DSP than in analog?
That's another lengthy discussion. Originally, we were designing the 8200 to pretty much model what we had done in analog processing. We were able to take advantage of a few things that you could do in DSP, particularly phase linear filters that were impossible. But the limited number of machine cycles available from the early 56001 DSP chips limited what we could do. And at the same time, I needed to educate myself. So I bought some DSP textbooks and read some papers and learned to get comfortable in what we call the Z plane as opposed to the S plane in analog. We originally had hired a DSP engineer. I learned quite a bit from him. But eventually I was able to do a lot of this stuff on my own. Meanwhile, computers got faster and faster, so I started actually prototyping DSP algorithms in Fortran, of all things. And I have a development system that allows me to do real-time processing. Fortran creates a DLL, and that's called by a C console application. So that is really great because you can make changes, you can recompile in a matter of seconds, and you can listen to the results. You don't have to worry about a hot soldering iron. You don't have to worry about plug boards as we used to do with resistors and capacitors. So from that point of view, it has been very liberating. And it's also been liberating in the sense that we could do things that were so complicated that if we had tried to do them in analog, we never could have built a reliable processor. It would have just had too many parts. Gotcha. So now that DSP design techniques are, another 10 or 12 or 14 years old from when you were designing the 8200, what conveniences have come about for you now? Can you do a whole lot more now than you could with your design tools of the 8200? Yeah, we certainly can. The new limiter technology in the 8600 takes far more machine cycles than the entire 8200. I think I worked it out, and there's something like 25 times the DSP power in an 8600 that there was in the 8200. So, it's been liberating because virtually anything you can imagine now, you can put in DSP, and you can make a processor that will sell at a price that the market will bear. The constant reduction in cost of DSP has been extraordinary, and it is, just been a great thing for me as a designer. I certainly do not have any analog nostalgia. I would never want to go back to the constraints of analog when it comes to doing audio processing for radio or digital radio, the internet, etc.
Well, certainly there are some folks who do have analog nostalgia. They love it, and one of them is one of our fans and friends of Bill Sachs. And of course, we all kind of get a warm heart when we see a device with glowing tubes in it. That's always a fun thing. Unfortunately, I got to pause right now and tell you that we're going to continue our conversation with Bob Orban. And we've got some great questions and comments coming in the chat room, and also Chris Tarr, I believe, is going to have the next question for us. But we're going to take a quick listen to a message from my employer and the sponsor of this episode of This Week in Radio Tech, and that's Telos Systems and the Telos HX1 digital telephone hybrid. You know, Telos, well, the phone hybrid was the very first thing that Steve Church experimented with and built back in the early 1980s, 83 or 84 or so, and ended up becoming a commercial product. You know, not so different than Bob Orban's own experience in the processor field some years before that. Well, technology's come a long way, as Bob indicated, that DSPs get more and more powerful, and also our knowledge of just what the little things, the little frustrating things that we're still dealing with in processing something seemingly as simple as a phone call. We're getting better and better at that. And the Telos HX1 honestly represents the highest and best from Telos in terms of processing a telephone call under a huge variety of conditions. Whether you're talking to somebody halfway around the planet or a cell phone on the next block, the challenges are quite different in these different scenarios. And yet the Telos HX1, its DSP technology and the software, the firmware that we put in there is able to deal with these differences in phone connections. You know, we still have to send a little burst of noise, very special burst of noise that Telos sends to the caller to see what comes back from what is reflected back from the various analog or digital hybrids along the way to that caller. And then we're able to do an extra good job of nulling out those reflections that come back. So when a disc jockey is talking, when a talk show host is talking, when the sports show host is talking and talking to the caller, you don't hear any of that audio coming back from the caller. And that's always been the problem with phone lines, is getting rid of this audio that comes back. And the figure of merit that we're talking about here is something called trans-hybrid loss. And through, honestly, a great engineering and a few little tricks up our sleeves, we're able to achieve an enormous trans-hybrid loss, even on POTS phone lines, even on long-distance calls, and even on calls going to people who are using, say, a VoIP service like Vonage, or they're using a cell phone, and there's a lot of delay involved. I should add that the Telos HX1 has an extra long time period that it analyzes the call, something that the earlier Telos hybrids, like a Telos 1, weren't doing, because those were developed in the days before there were digital cell phones and VoIP calls, which do add that extra delay. So check out the Telos HX1 on the Telos website. There's the HX1 and the HX2. The one is obviously one telephone hybrid. It's got room to plug one phone line into it. You can also plug a phone set into it, so you can make your outgoing calls or talk to somebody not on the hybrid. Then there's the HX2, which has two Telos hybrids in it. They also can be cross-connected internally for conferencing. So you can actually supply just one mix-minus audio from your console into a Telos HX2, and say caller A will hear your mix-minus plus caller B, because that's done inside the HX2, and caller B will hear the mix-minus audio plus caller A. So they're conferenced without having to have an overcomplicated audio console that's providing two mix-minuses and maybe some complicated wiring too. So check it out, the Telos HX series. Oh, these have processing in them, some audio processing, and some extra tricks to really reduce the chance of feedback. For example, the audio that's sent to the caller is actually pitch shifted downwards by a few hertz, so as to reduce the chance of audio, acoustically coupled feedback from the other end. Hey, if you're in a TV studio, you have open mics and open speakers, the Telos HX1 works great in that environment as well. Plus, it does handle the variety of telephone standards, POTS telephone standards around the world. The chipset in it is designed to work with just any country you can name. There's a dip switch setting to handle the voltage, the ring cadence, the dial, the battery voltage, whether it's reversal or not, all those different things, the loop current, the interrupt cadence, all that stuff is built right into the HX1. And at the end of the show, we're going to give one of these HX1s away if you have retweeted my announcement that the show was going to start, or that Bob Orban was going to be on the show. I made about 4 or 5 announcements today on Twitter. If you follow me at Harnack and you retweeted, you are eligible to win. So we'll find out who the winner is in just a few minutes. All right, on with the show. Let's hear from Chris Tarr. Chris, you had, I think, a question for Bob Orban. By the way, Bob Orban is our guest, and he's with the Orban Audio Processing Company at orban.com. Chris, go ahead.
A question / comment. I think one of the things we were talking about a little earlier with audio processing and program directors and things like that, I think one of the things that we run into nowadays is we now see with the digital processing and the cleanliness that it brings, that what kind of was a signature sound, let's say, back in the 70s and 80s, was really a whole lot of distortion. It was making, creating square waves and rolling audio off at, sometimes depending on the components used, 12, 13 kilohertz, bad audio, bad exciters, that sort of thing. And I think one of the challenges, and I guess that's the question part for Bob, is I think probably one of the challenges has got to be the fact that, in the 60s, 70s, 80s, we had this big wall of sound. Unfortunately, that wall was a whole lot of distortion based on everything being cranked up and the lack of cleanliness in the audio. And it was a challenge for me is kind of retraining our program directors that loud, there's a difference between that kind of flat brick wall, rippling loud and a nice clean loud. And I remember when I went from my first time I went from an analog processor to a digital processor, the very first thing they said is, wow, that's stunning. The second thing is, it just doesn't seem quite as loud. When actually, if you look at it, it was. And after a couple of days and they got used to the difference, they realized, yeah, actually, that's, there's some dynamics there. I was just wondering, Bob, when you first came out with, probably not as much the 8200, but say the 8400, were those some of the comments you got? Like, it was just, it's almost like it's a totally different way of doing things now, a totally different sound.
Well, yes and no. There's plenty of ways of creating a wall of sound without using a lot of clipping. When you have a 5 or 6 band limiter and you get into it heavily and you use fast release times, you can get a sort of compressor wall of sound that has its own problems, I think, in terms of fatigue, but it doesn't necessarily sound distorted in the way that clipping distortion does. So it's just a different set of tools in the toolkit. But, one message that I would have for program directors or anybody else who wants to overprocess is simply that when everything is loud, nothing is loud. Because loudness only exists as a relative sensation compared to quiet. So getting some dynamics back into the program, I think, is a very positive thing. I think it is likely to keep people listening longer, and I think it is likely to be more musically involving. It's more likely to get listeners more emotionally involved with the broadcast.
I think I sometimes compare it to salt. If you put a little salt on your dish, it tastes really, really good. Put a lot of salt on your dish and it tastes awful. So I think, audio processing is kind of the same way. A little bit, it goes a long way. And I always like to kind of practice addition by subtraction. And sometimes you can get a much louder sound actually by dialing things down just a little bit and putting in a little more dynamic range. So I just know the difference, especially between the progression between the 8100 through the 8500. It's amazing the things I can do now with an audio processor that I couldn't do back then. The type of sound I can create that still is very powerful yet. And I know the Omni 11 and even the Omni series is very good at this, creating a very open sound yet very stunning and jumping through the speakers kind of thing. And I think the world is certainly better for your designs and for Frank's designs and the evolution of DSP, because we went from having fairly low, for the time it was pretty progressive stuff, but you listen to the progression in audio quality over the years and FM especially, sounds so much better now with the quality of the audio processing we can do now and the tools that we have at our disposal. It's just interesting to see how that's progressed over the years.
I got a question for Bob. Bob, in some forums, you have mentioned from time to time that you like to go to classical music concerts to calibrate your ears and to kind of remind yourself of what what the real world sounds like. How does that practice? How can an engineer use that practice to evaluate or calibrate his ears for his own radio station in light of the real world dynamics of we got to be loud, we got to be bright, we got to be dynamic. How does that work?
I think it is almost two different things. The calibration of one's ears with acoustic music shows you basically the ideal, where there is no electronic amplification at all. Even if you go out to a jazz club or a rock club, you're likely to hear a lot of electric instruments, and you're also likely to hear a PA where the individual sources have been mixed together. I grew up with classical music. I did a classical music show for 4 years at the student radio station, and it sort of sets the end stop, if you will, for what can be done musically when there is almost unlimited amounts of dynamic range and absolutely no electronics that get in the way. I think that anybody adjusting a radio station, though, also has to go to a live rock or jazz or rap, hip-hop, raves, whatever, just to get used to what people are listening to that's not on the radio. And somehow you need to try to integrate all of this stuff and use it to calibrate your taste when you're finally setting up the processing.
Can you adjust processing, and can you develop algorithms while listening to music you really don't like?
To a certain extent, yeah. After a while, I start listening to the problematic parts of the music technically. I have a whole bunch of stuff that I use over and over again because I am very familiar with things that can go wrong. I don't think I would ever listen to that music again for pleasure. But it's just a different way of listening, and some people say that are we on, because it looks like, okay, there, we're back.
We are streaming.
Did we miss any of that?
If you back up about maybe 15 seconds, I think nobody will miss anything. We are back. Sorry.
Okay.
We were talking about music that you don't like and music that
right.
breaks the processor.
We as processor designers tend to get into this mode of listening to sound for its own sake as opposed to the musical aspect of it. But I'll say that one thing that I do not feel that a processor is finished until I can actually run my test material through it and can enjoy listening to it. Some of this is just sort of, I think, subconscious. It comes from, my own particular preference and long experience, and who knows what else.
Earlier, you mentioned about crossovers and how we understand that for a long time now we've been doing multi-band audio processing. So there's a little man with a volume control on the bass and a little man with a volume control on the mid range, and so on for the upper ranges. And I've heard you and I've heard Frank Foti also talk about the design of crossovers. Why is that so important, and what's one of the first mistakes that a newbie designer could make if he were designing a multi-band audio processor?
Well, I don't want to give too much training to newbies, because the next thing you know, they're oldies and they're competing with you. But I think that it's a matter of looking at the details and reading a lot. There's two essential categories of crossovers. There are all-pass crossovers and there are phase linear crossovers. Both of them have a flat frequency response when all of the bands have the same gain. All-pass crossovers, however, introduce an overall phase shift into the sound, whereas phase linear crossovers do not. Frank Foti and I have disagreed with this or about this over a number of years, but one of the secrets of the fat OPTIMOD sound is the use of all-pass crossovers. I can say that. Mm-hmm. And it's no secret that we have done that ever since the days of the 9000.
Well, I guess kind of related to that, because you've mentioned all-pass a few times. Can you help me understand what an all-pass filter has to do with removing asymmetry, and why do you want to remove asymmetry in an audio processor?
Leonard Kahn, I believe, accidentally discovered in the course of making single sideband transmitters that the 90-degree phase difference networks that you needed to make analog single sideband transmitters also had this fortuitous side effect of making the waveforms of speech more symmetrical. And he came out with a product called the Symmetropeak, the first all-pass phase scrambler to deal with vocal asymmetry. The reason that it's good to do this is that applying an all-pass filter to a signal is the closest thing you get to a free lunch in audio processing, because it's a so-called linear process, meaning that it doesn't introduce any new frequencies into the spectrum. Many voices are asymmetrical by as much as 6 dB. In the old days of AM, where you had an unlimited amount of positive peak modulation permitted by commission rules, some people use phase flippers that would automatically move the positive peak so that they modulated the transmitter in the positive direction, but FM does not have that. And moreover, at least in my experience, it turns out that applying an all-pass phase scrambler to make speech more symmetrical before a clipper sounds better than even taking advantage of AM asymmetry. And considering that the audible effect of these things is really very, very subtle, unlikely to be noticed by any everyday radio listener, it's pretty much a win-win.
Okay. All right. We're going to have to wrap the show up here pretty soon, but Bob, I wonder if you might give us your thoughts on processing, like right now, and where it's going. And I guess we're really talking about processing for codecs. This has become such an area where processor manufacturers are trying to make some headway and trying to persuade users of codecs that you need to process to get the most efficiency out of that codec so it sounds best at the other end. What are some of your big initial thoughts on that, and where do you think we're going?
I think that the most important difference between processing for today's codecs and processing for AM/FM is the peak limiter technology that's used. The peak limiter technology for AM and FM is based on clipping in some sort of fancy way, often with psychoacoustic models or other elements to remove as much of the distortion as you can. But in the digital radio or internet processing, we use look-ahead limiting, mostly because the modulation sidebands that are produced by the gain reduction are very close to the unprocessed Fourier frequency components in the unprocessed audio. That means that they stay within a psychoacoustic critical band of the unprocessed audio, where that is typically 1/3 of an octave. It means that unlike a clipper where you're throwing extra grunge throughout the spectrum, the psychoacoustic model in the codec does not have to try to encode this extra clipper distortion, because with a look-ahead limiter it's not there. It used to be that there were other tricks that were useful for dealing with very low bitrate codecs, particularly the old Windows Media and so forth. But with the advent of spectral SBR, spectral band replication technology used in HEAAC and in the HD radio codec, that has become less and less important, because the high frequencies now get reconstituted in a much more efficient way than the older technology allowed them to be.
Okay, that's I hadn't thought about that. It's an interesting take, and I'm sure you're right. So, is the bottom line that it actually becomes a bit easier to process for codecs because they're using spectral band replication?
Yes, absolutely. It gives the broadcaster much more artistic leeway in how the processing is set. It's still wise to try to keep density fairly loose, not use very fast release times in the compression, because I think the codecs do respond better to open sounding processing. But I have to say that at this point there's a real problem at the mastering side, and it's gotten to the point where I buy CDs and I think, why did I do this? Because the last one I bought sounded horrible. I couldn't stand to listen to more than 2 cuts at once, and now this one does too. As you know, Frank and I wrote a paper together called What Happens to My Music When It's Heard on the Radio, I believe, or something very close to that, where we described what happens to a CD when it is broadcast. And the bottom line is that what the industry really needs is radio mixes, or I should say radio masters, where everything is the same except the mastering engineer just pulls back the drive level to his clippers and his digital limiters by 6 dB. And then you have a radio master that basically has all of the coloration caused by compression and equalization, whatever the mastering engineer puts in, but it is clean, and it's going to work much better with transmission audio processors on the radio.
That is a wonderful idea. Do we ever have a hope, a dream of getting that to happen industry-wide? Have a radio mix? I mean, that's not just a shorter version, but actually is a better sounding version.
Well, I would hope that somebody like Clear Channel could come to Universal Music and say, hey guys, you're causing us a lot of problems, and all you need to do, and it wouldn't cost very much, is to tell your mastering engineer to make two takes of this, once at +6 and once at 0, and it's going to help sell your product a lot better on our radio stations, and it's going to be better for deal for everybody all the way around.
Yep, you're right. Bob, I'm afraid we are absolutely out of time. We've used every last second that they're going to give us, and we were going to have to go. My co-hosts on the show here have been Chris Tobin from New York City. Chris, thank you for being with us and adding to the show.
Oh, you're welcome. You're welcome. It's an actual pleasure, and all the years I've done audio and worked in and out of transmitter sites, let's just say one constant has been the OPTIMOD, and I know of many folks who would kill to get an OPTIMOD back on the air, the old analog ones as well, wherever they can. So, Bob, it's an absolute pleasure, and genius behind your work is a test of time.
And Chris Tarr, is Chris Tarr still with us to say goodbye?
I am. It has been a pleasure. I've been a fan of Bob Orban's for years. I've been following his work, and I'm like a little kid getting to talk to him tonight. So thank you, Bob, for joining us.
My pleasure.
It has been great. Bob, thank you very much for coming on, and appreciate the fact that maybe Bill Sachs had some influence in getting you to come on, and appreciate your drive up to Petaluma this afternoon. Thank you very much.
Quite welcome.
All right. Well, thank you for joining us on This Week in Radio Tech. Our show today has been brought to you by Telos at telos-systems.com and the Telos HX1 telephone hybrid. Now, we're going to give one away right now to folks who have retweeted, and we got to do that real fast. Bob, I need a random number from you. Do you have your random number generator ready? I need a random number between about 1 and 42.
I will take 29, since that's been my preferred birthday for a long time.
All right. All right. Let's see. 1, 2, 3. No, we're not giving it to Chris Tarr. Thank you for retweeting, Chris. I appreciate that, but we're not giving you the... All right. Here we go. I counted... Oh, my goodness. Wow. Apparently a deserving Twitter user. Congratulations on winning the HX1 to Toby Mai, who goes by Grumpy Tech, at Grumpy Tech. Retweeted this to over 3,000 followers. Thank you very much, Toby and Grumpy Tech. And why don't you send me an email? I'm easy to find, or send me a direct message on Twitter, and I'll get back in touch with you, and we'll get you your Telos HX1. Thanks again for playing along, and thanks for your attention. I think we're off next week, but we'll be back the week after with another great guest, or maybe just 3 or 4 of us chatting about broadcast engineering. That's it for us. Burke, thank you, and thanks to all the people. We thank you, and we'll see you next time on This Week in Radio Tech. Bye-bye.